In this paper, we present the heading control and a long-endurance flight of a soft-actuated micro-aerial robot. Natural insects can demonstrate exquisite flight maneuvers, which inspires researchers to develop at-scale flapping wing robots for flight. While piezoelectric actuator-driven robots have shown astonishing achievements in the past decade, the newly emerging soft-actuated micro-aerial robots, such as MIT SoftFly, have gathered more attention in recent years. The MIT SoftFly, which weighs less than a gram, is actuated by the dielectric elastomer actuators, or commonly known as the soft artificial muscles. With these soft artificial muscles, the SoftFly demonstrates remarkable resilience to collisions and can execute aggressive maneuvers such as somersaults. However, this soft-actuated robot still encounters two challenges that are commonly faced by the insect-scale drone. First, the lifetime of the mechanical components is extremely short. And, second, the lack of yaw control authority. In this paper, we improve the mechanical hinge for longer flight endurance, and we modify the robot's configuration to control the yawing angle. We first look at the challenge of components' lifetime. The failure of mechanical parts prevents insect-scale robot from flying for more than 20 seconds, and the hinge is usually the component that fails the entire system. To redesign the wing hinge, we first look into the flapping dynamics of the actuation, which consist of two degrees of freedom: the stroke angle, which can be actively controlled by the actuator, and the pitch angle, which is passively controlled by the hinge stiffness. The hinge is the component that connects the wing to the robot. The meticulously chosen stiffness has great influence on the flying performance and cannot be modified easily. So when we encounter failure during flapping, we can't arbitrarily increase the thickness to reinforce it. Herein, we propose to use a 3-layered design to replace the original 1-layer hinge. The figure at the bottom shows the comparison of the two hinges, which is a zoom-in version of the cross-section view of the dashed line contour in the figure above. The 3-layered design composes of one inner layer, which connects the wing to the body, and two outer layers that control the stiffness. The outer layers do not experience bidirectional bending, which mitigates fatigues. We found the new 3-layered hinge achieves a similar flapping motion to the original one, and the lifetime is significantly increased by 182%. We then subsequently conduct a 40-second endurance flight with the new hinge. The robot completes the flight without hinge failure. To the best of the author's knowledge, this is the longest flight carried out by a subgram aerial robot, and the flight time is 2 times longer than the state-of-the-art rigid-driven robot. Then, we turn our attention to the second challenge, the lack of yaw control authority. This shortcoming prevents the robot from conducting directional sensing, like visual inspection with a camera, and compromises the performance of some controllers. We start by looking at yaw torque generation on the quadrotor and compare it with SoftFly. Both the quadrotor and SoftFly have 4 thrust vectors. However, the quadrotor can generate yaw torque through the conservation of angular momentum, but SoftFly cannot produce net yaw torque due to the time-averaged lift force. To address this problem, we design an inclined stroke plane that tilts each unit inward by 20 to 25 degrees. With this new configuration, we can now generate forces not only in the vertical direction but also in the horizontal direction. By increasing the actuation in unit number 1 and 3 in the figure, we can generate positive yaw torque without influencing the pitch and roll motion. And the negative yaw torque can be generated in a similar fashion. Through leveraging the bidirectional yaw torque generation and a PD controller, the SoftFly achieved a 12-second flight with desired yaw angle set to 0. The root mean square error is 5.6 degrees, and this task was carried out 3 times for repeatability. Lastly, we conduct a 10-second flight for SoftFly to track a yaw trajectory. The robot completes the task with a root mean square error of 5.8 degrees, which is comparable to the state-of-the-art rigid-driven subgram robot. These flights show that SoftFly can effectively regulate the yawing motion in flight. We can now compare the development of the SoftFly to the rigid quadrotor. There are 3 stages of development for drones: the mechanical design, the low-level model-based control, and high-level advanced control algorithms. The quadrotor nowadays leverages reinforcement learning or model predictive control to track aggressive trajectories, but the reliable generation of roll, pitch, yaw, and thrust is still a prerequisite for implementing these advanced controllers. On the soft fly side, the advancements in the past 4 years have focused on improving the actuator. The yaw control and long-endurance flight in this paper complete the model-based control in this roadmap by independently controlling roll, pitch, thrust, and yaw. This milestone allows us to directly utilize some of the well-developed advanced control algorithms from the mature quadrotor community to possibly enable more agile, robust, and precise flights in the future. In conclusion, we developed a new 3-layered hinge design which prolongs the lifetime of the mechanical parts and enable a 40-second long-endurance flight. Then, we use the inclined stroked plane approach to generate yaw body torque on the soft fly, and subsequently conducted the yaw-controlled flight with setpoint and trajectory tracking. In summary, these improvements have made soft-fly more reliable with an additional degree of control authority, paving the way for implementations of more advanced control algorithms in the future.